Hello and welcome to today's webinar. Thank you for joining us. My name is Irshad Hanif, and today our topic will be getting started with Inventor Tolerance Analysis. We're just going to wait a few minutes until more people can join if they're going to, and then we will begin. Okay, I think everybody has joined now, and without further ado, we can begin. So, Inventor Tolerance Analysis. Let's firstly discuss our agenda for today. We're going to ask the question, of course, what is tolerance analysis? So those of you who are new and have no idea about inventor tolerance analysis as a tool set and what you get, we're going to discuss what it is. We're also going to take a look at why you should use it, or in case you're wondering why anyone would want to use it, or what sort of problems manufacturers and designers and engineers have when designing parts that fit together. We're going to take a look at where to get it. It's not obvious as to where you find it. It's not something you can just simply Google and get. You will need a product design collection, etc. Then we're going to do a quick demonstration, some examples, and at the end, we're going to take a little session, or we're going to set aside a few minutes for a Q&A session. So that's basically our agenda for today in this quick overview and a short webinar. So, what is inventor tolerance analysis? Well, basically, inventor tolerance analysis is an add-in for Inventor that exists in the Environments tab. So you'd have to download and install this add-in, and it is designed to help clean up design specifications. So if you look at things like gears and cogwheels and bearings and brackets that fit together in a tight space, when manufacturing these components, they can be manufactured not 100% all the time. So, for example, if you think of something that's 10 moles and needs to be machined or manufactured at 10 moles, it's not going to be exactly 10.000 millimeters all the time. It's going to be 10.1 or 10.5, depending on your manufacturing process. Now, the problem comes in when you stack all of these things up together. The combined effect of all those tolerances either being higher or lower than what it's supposed to be is going to have an effect on the space that it's fitting into. Okay, it provides a 1D analysis option, meaning that it can analyze the various tolerances in a single axis or a single direction. But you can have multiple directions there. So what that means is it cannot do 2 dimensions at a time, but you can have multiple stack-ups of 1 dimension analysis. I know this may be hard to understand just with the slide and without a visual example, but hopefully when we get to the physical demonstration, I will show you visually what that means, okay? So you will find that the tolerance chain through a single loop can be calculated automatically in that 1D analysis workflow that Inventor Tolerance Analysis has. Okay, and just to reiterate, we can do, even though it's a 1D analysis, we can do multiple stack-ups in an assembly. So you can do a 1D analysis in your X direction, for example, and then you can do a 1D analysis in your Z direction, as an example. Okay, so what are the causes of dimensional variation? Like I just spoke about earlier, is that we know that different manufacturing processes have various sort of tolerance values. That depends solely on the nature of how a part is made. So for example, machining might be a little more accurate. You're working with 0.1, 0.005 tolerances, depending on the part and depending what type of method you're using, whether it's a CNC machine or a milling machine, or whether it's a very skilled artisan who's working on a lathe, for example. So those are things that will affect your tolerances or it will give you dimensional variation. Other such things are things like tool wear. So if you're working in a machine that cuts out your parts, the wearing of the tool will cause variation. When the tool is very new, it will cut very sharply and very precisely, but as it's being used, it will start to be less accurate and then leave some dimensional variation. Um, Operational temperature is another factor. So if you're, for example, molding or cutting stuff, and it tends to heat up or cool down, we will know that those kind of things play a role in how the size of your part, especially if it's something like a hot plastic mold, it would expand or retract depending on the molding process. Okay, we've also got things like component deflection. So as things are bent or loaded, or they start to move um, as a result of these loads. Then I spoke about machine precision. Like I said, your CNC or your manual lathe. Operator setup. So if there's an operator controlling an automated machine to make certain parts, and he does not load the source or the stock material up in the correct position the same time for that manufacturing process, if he does not load it up in the same way or at the same location, which there normally is in most manufacturing processes, you're going to get some dimensional variation. Okay, and the last one, of course, is you will have movement during machining. So, like I said, that can be technically linked to operator setup, or maybe just the part that you're trying to machine is really, really long, and as you're machining it, it starts to wobble at one end, or maybe if you're not using a tailstock for whatever reason. So things will happen where um, you will end up with some sort of inconsistent dimensions. So why should I use tolerance analysis? Well, basically, we want to reduce the number of physical prototypes that we make. So when we're designing a part for the first time, we want to make it perfect as possible. So we will use the highest standard of quality to make sure that the first part can be tested properly and make sure everything fits. But of course, we want to repeat that multiple times. If you're making a very high volume product, you want to account for the various tolerances such that you don't end up wasting a lot of money by having lots of your parts unable to fit in your assembly. Okay, it will also increase product performance, increase product quality, and like I said, it will reduce cost, therefore increasing profitability. Okay, so what we'll be able to do is increase profitability, meaning that you can identify where to apply high-end tolerances uh, and use very expensive machining methods, and you can identify where to use low-end tolerances where you don't really need that to be very accurate, and you can say, well, just make it as cost-effectively as possible. Okay, this also allows you to avoid costly consultation and engineer fees to assess the design for you. You can do it yourself using Inventor's built-in tools. Okay, so let's move on to the next slide. Still dealing with the same topic. Why should I use tolerance analysis? Um, like we said, it would save you on costly consultation fees with engineers, but also it's integrated with Inventor. So you don't need a separate application to go and open and export your Inventor model and then open it in a third-party software and analyze it and then bring it back to Inventor and then sort of generate reports. Everything is integrated into the Environments tab if you have the Product Design and Manufacturing collection. Okay, so it offers 1D analysis. Like we said, it will check things that are stacked up in one particular axis, either your X, your Y, or your Z, or whichever axis you want to go in. Um, it allows you to do multiple 1D analysis, so you can do multiple stackups in a particular direction or in many different directions, but we will not take into account two directions at the same time, meaning we will not do 2D analysis. So we've got to be careful there. Okay, it will do automatic calculation of cumulative effects of geometric dimensions and tolerances. So basically, it would use a whole bunch of scenarios to calculate the effects of those dimensional variations, and it will basically give you a count of, okay, for example, if you make 100, you have a chance of having maybe 30% of them that are not going to be within spec and unusable, basically. Okay, the types of analysis you'll be able to get out will be CPK, sigma, DPMO, and percentage yield. So those are just some of the metrics that you can use to track in and out of spec percentages. Okay. Then it has a tool to report a generation, to do report generation for your engineers and your quality assurance staff. That would be very useful to tighten up your manufacturing process, especially in a processing plant that's making high-end or very technical components. You really, really want to identify your places of improvement in your process engineering department. Okay. So where do I get this tolerance analysis tool from? Well, if you go to your Autodesk account at manage.autodesk.com, you will be able to find your whole list of products under all products and services. And just as with everything else you have, Inventor Professional, Fusion, whatever else is included in your collection, you will see a separate section there for Inventor Tolerance Analysis. You've got to download the same version of Inventor that you have, so make sure you do that. Your versions must match. And just to reiterate, I've said it before, it is only available with the Product Design and Manufacturing collection that you would get from your Autodesk supplier. Okay. You'd want to basically click the download button, choose your method of download, and install it. You got to make sure that all your Autodesk products are closed. So don't have AutoCAD, don't have Inventor, don't have, I think Outlook as well sometimes interferes with installations. So don't have any of those things open and just install it. And it isn't a very big download, nor is it a very big, long install. You can just install that, and the next time you start Inventor, it should be available in your Environments tab. Okay, so we're just going to, at this point, it's time for a quick demonstration. All right. So basically what I've done is I've separated our demonstration into two parts. Right, I've got part A and part B. And part A, I just want to cover, for those of you who are very new to all these kind of topics, basically where the tolerance settings are in Inventor and just understanding how they work without even getting to the tolerance analysis tab. And part B, I will take you through the tolerance analysis workspace, and that will be more on point or more relevant to the topic of this webinar. But I decided that it won't be relevant if, like I said, some of you are very new and you don't understand where these tolerances are to begin with. Okay, so with that being said, let me just bring in my Inventor to the main presenting screen, and there we go. I'm sure you all can see my Inventor now. So we need to start from the very beginning. Like we said, in Inventor, if you there are things called dimensions, as we know. But of course, with your dimensions, we have an added bit called tolerances. So if I go in here and I start a very simple sketch, right? For example, if I'm just going to project my x-axis, and I'm going to use a rectangle, and I'm going to say, right, I'm going to perhaps 150 and perhaps 60. Okay, something like that. I'm going to make this symmetrical about my y-axis. Let's get it there. And I'm just going to make another. So it's going to be okay. And I will do the same for that. I will make that symmetrical about the center as well. So basically that little U shape is what I want to make. Now you'll notice that I've entered dimensions on my sketch, and you notice that they are fixed dimensions. If I go to my parameters, you'll see that whatever dimensions I've created, as per usual, go in under model parameters because I've entered them in this particular model, and they give me a little line item here telling me, okay, what is the equation or what is the value of it, its nominal value, and what its tolerance is set to. Now just keep that in mind, because each of these dimensions, if you went to Word, you could right click on them and say dimension properties. Here you'll be able to give it a name just as you were able to under the parameter section. So for example, I could say length, but more importantly, you can give it a tolerance. So you can say, well, yes, it's going to be 150 mils, but symmetrically, it's going to be 5 mils either greater or less, or perhaps not 5 mils. That's a lot of tolerance, but maybe 0.1 mil. So it's going to be either 150.1 mils or 149.9 moles. So that's the level of the tolerance. So I can say, okay, you'll see here on the evaluated size, I have the option to do a median where it does somewhere in between the max and the min. Right, so that directly in between there, it can do the upper limit, which is 150 plus the 0.1, can do the lower limit, which is 150 minus the 0.1, or it can do the nominal value. Okay, I'm going to leave it as so, and you're going to see as I do that, it changes, or the display of the dimension changes to show you just not just the value, but also the tolerance. Okay, I can do that with, for example, my height as well. I'm going to say right, and again, let's do that again, and we're going to make it, well, let's say 0.5. 0.05. Okay, so now we have some tolerances assigned to that. So let us extrude the shape out, and we'll play around with the types of dimensions. I'm going to put it both directions. I'm going to say OK. I'm going to right click and say show dimensions. So if you're not familiar, that is an option in Inventor to always show the dimensions of your extrusion. Because remember, as you use up a sketch or you create an extrusion from a sketch, it automatically makes it invisible. So you do have the option to show it if you need to see it always, like now. Okay, so let's go back to our parameters, and we can see that I have now the option to change some of these tolerances. So let's say if I make it on the upper limit, and I make that on the lower limit. Actually, let's just show dimensions again. So what do we think will happen for these sizes now? So let's just measure that. We said that was the upper limit, and indeed it is. It is 150 plus the 1. Let us check the height of it. It is indeed 60 millimeters minus the 0.05. And so that is basically how we're able to leverage the tolerance tool in Inventor. So that has nothing to do with the tolerance analysis section, but just using the tolerance option in your dimensions settings. Okay. Now, what happens if we want to create an analysis of this? So, for example, I'm going to perhaps let us start a sketch here, and I'm going to project maybe that line. I'm going to extrude that shape. I'm going to make it a new body. Now, let us just do something like this. I'll say, yeah, that looks about right. 50 mils. So that's a separate extrusion. And I'll do it again. I'm going to extrude a new body as well. And I'm going to go all the way up until or rather I should say 80. I'll give it a dimension. Okay. Now, that's fine. Let us go in and edit the show dimensions. So we can right click on that dimension, show dimension, and we can say dimension properties, and we can do the same thing. So remember, it's not based on a sketch anymore, it's based on the extrusion length. Okay, and I can say, let's make it 0.25. So it can be 0.25 of moles greater or 0.25 moles less than what it normally is. We'll do that to the other side as well. So we'll say show dimensions. You can right click on that, dimension properties. I'll give it a, I will continue to use symmetric. Remember, there are many different types of tolerances that you can add, but for simplicity, I will just use the simplest symmetric option just to indicate that it can go either bigger or either lower. There's obviously minimum, maximum limits for fit stacked, fits linear, etc., etc. Okay, I'm going to say that one is, let's say, 0.1. Okay. Now, the reason I did this was because I'm still in a part. Now, your tolerance analysis, even though the option is here under environments, it is only available in an assembly. So right now I have a part. Okay, so I've made my part with all my different tolerances, and I need to create an assembly from this in order to be able to use my tolerance analysis tool. So I will go to manage. I'll say make components. It's asking me to save first. No problem. We can do that. Let us go in and say test part. We'll call that my part. Okay. We're going to select exactly what defines this part. All right. We're going to select the template or the assembly template, etc., etc. I think I'm happy with that, and I will say OK. And just like that, we've got an assembly now. You can see my part IM with 3 different parts in there. Okay. Remember, it's still manipulatable by this initial IPT that it's linked to. Let me just change my view to that. At this point, I now have 3 parts that are fitting together, and remember that each of these parts, if I open them individually, for example, they have its own, well, actually, I should show you in here. Each of these parts has its own dimension attached to it and its own tolerance attached to it. Okay, I'm just going to close that. So now that I have an assembly, I can actually go to my Environments tab and go to the Tolerance Analysis tab. So now we're entering part B of our quick demonstration as part of this webinar. Okay. Basically, we're going to take a look at the add-in itself, the tolerance analysis add-in. So I'm going to start by going into the environment, and you'll see that it takes me into a totally new space where I still have my model tree on the left, but it has this new window on the right. And what you're able to do here is create a stack up. It's sort of like creating a study. If you've done FEA or basically any other Inventor workflow, you create a new setup for that particular analysis, and it will be able to calculate things for you. So how does it work? Let's try on this very simple part, creating a new setup. So the first thing it wants to do is define the gap space that you're working with. So in this case, I want to define that, I want to choose that outside face or that inner face there. Yeah. Right. And then I also want to choose that. Right. So basically that I'm telling Inventor Tolerance Analysis tool that that is my leeway gap, or is that is the critical dimension that I need everything to fit in by. So it's going to calculate based on that. So if there were a gap, you'll be able to see it. The next thing is awesome for annotation plane, basically where to display those dimensions. So I can just look at my origin and say, well, not there, not there, there's good. And you'll see that it will start to display that gap. Okay. And then what it's going to do is it's going to look for components that are stacked together, and sometimes it will find automatically. In this case, it doesn't, but for example, there is an option here to do the automatic selection of a stack up. In this case, it doesn't find any, so I'm going to pick the components. Yep. And I'm going to say, yep. So that's fine. And I can tell it exactly which component is where. So obviously, I need to define the faces of my design. So I need to define, like we said, when we do a new stack up, we're going to start there. And then we're going to tell it there as well. I can select other. There we go. So that's our initial. I'm just going to do this from the scratch again, as I had issues before. Then I'm going to find my annotation plane, which is, it's going to be my y x-axis. Okay, and I'll do that. Okay, now it's looking for my first component, and then it's going to look for my mating faces of that first component. So it's obviously going to look for where that component is mating. Oops. And then I can give it. Now, once you've done all of that and you've picked all your components, it's just not working quite right. So I just have a backup here of how it's supposed to look. But once you've done all of that and you pick your faces and you tell it which component is mating with which component, it should be able to give you a finished result like so. So I will show us on the little backup that I have. Like any good webinar, it's nice to have a backup in case things don't quite go your way, as we see now. But basically, I will do it with this pre-driven model, and this one fortunately is drawn in a way with some forethought where it allows us to automatically select a stack up. So I'm going to go do that same process, new stack up. I'm going to tell it, well, the gap that I wanted to analyze is between, or the gap that I wanted to base it on is between there and there. I'm going to choose my annotation plane as my YZ. Sorry, my XZ. I have to do that again. Sorry, I just wanted to look neat on the correct axis. The annotation plane is just for a display, really. There we go. That's what I wanted to do. Right, and then you'll see that of the two methods, one is selecting the components, which didn't quite work out too well. Like I said, you got to have some forethought when designing your parts for the order. But the automatic option, where you say assembly constraints and joints, if they are assembled properly, it will detect a path. So let's say one path bound, and if you hover over that, it shows you, well, based on the assembly and these constraints, I can understand that these bearings and these clamps are stacked up in this way. So you can choose that one and say, okay. So once you do that, you can see that it automatically populates all the dimensions with the tolerances that you have set in the individual design. So you'll see your stack up is populated here. Remember, this is just one stack up that you created. If you go back here, you'll see that stack up one. You can give it a name, stack up. And if you go into there, that's it. Okay. So once we go into that one, we'll see that it's defined all the different dimensions and the various tolerances of the parts. So we can go in here and we can edit these things, and we can say, okay, I want it to be based on a plus minus or limits or etc. etc. I can even go in and change my tolerances. So let's say I want to make it 0.02. It recalculates everything and adjusts our analysis. So if you go right to the bottom, you'll see that you have my first, basically a summary of my first stack up, and it tells you there what it's based on. So we based it on this little gap here that we have. So the cumulative effect of all the different dimensional variations will have a certain effect of there, and we can say that I want a certain objective to have maybe 0 inches or greater than 0 inches as my objective. All right, you will notice two tabs here on the bottom. It will give you results and contributions. So what does it mean? Let's take a look at the results tab. Basically, if we can choose, if you look down here, there's a little arrow, like we discussed, to choose the type of analysis that it does. So we can say, I want to do a root square RSS analysis, and it would give me, okay, I have 0.03 inches to play with, and most of my designs take into account all of the tolerances of the various parts will fall in between there and there. And I have a criteria of 0, which is at that point. So you'll see that the entire scope of all areas are in the clear, they're in the green, and we're good. Okay, so we can say, what happens if you go 0.015? You'll see that if I make that my objective was to be greater than equal to 0.015, you'll see that of all of this, a certain percentage deviates and it goes beyond that. Right? I can use another method of analysis. I can go worst case scenario and say, okay, well, the worst case scenario is basically this. I'm going to get 0.014 inches out of spec. Right? If we go to the contributions tab, it shows me exactly which components there are guilty of the most variation, or the biggest problems rather. And we can see there that it's the shaft one, dimension 2 on shaft 1, and bearing 3, and it tells you exactly which dimension. They account for 45.5% equally of the total variation that we're experiencing. Okay, so you can see that it's very comprehensive in its analysis. Okay. So of course, like we said, we can go back and we can create multiple analyses and play around until we get the result that we want and finalize our design, saving you lots and lots of trouble making various prototypes and having your machinist, make multiple parts of various tolerances. At this point, you can decide, okay, well, if I'm experiencing that kind of variation, uh, my bearing, for example, contributes 45%. I need to make my bearing using a process that is very, very accurate, right? So once I'm happy with my stack ups, I can go and generate a report, right? But before we get there, I may have neglected to show you something. There's also a settings option where you can just define certain basic things. For example, if you're working millimeters or inches, you can define the standard tolerances for things that don't have a tolerance. So remember, in order to get these tolerance values here, you'd have to go to each of your parts. For example, here, um, let's go here. You'd have to open each one of your parts, right? You'd have to go and click on your dimension and go to show dimensions, or you have to go to dimension editor and base, or you can go from your parameters and edit all of these things here. So for example, I'm not sure where these are located, but basically you would need to go in and change to specify that you want a tolerance on these. However, if you go back to, let us go back to tolerance analysis, you can define, let's say, a standard tolerance on all that don't have any tolerances added to it. Okay, then you can set, obviously, I went down to in my options here and set the objective and the type of quality analysis type. You can set it as default, and you can choose the statistical quality metric, whether it's process CPK, sigma, percentage yield, DPM, etc., etc. Then there's some display option for your annotation and stack up color. Okay. Right. Where was I? All right. Generating a report. The last thing we can do is, when we're happy with this, is generate a report. And it's as simple as clicking the generate report button and perhaps saving it as, yep, or stack up report. I'm going to save that, and you will see that it will generate a report in HTML format. I'm just going to drag it up here, and this is what it generates. So it gives you your design assembly name. It brings up a table of your first stackup, whether it's okay or not. Obviously, in our case, ours wasn't, because I set our objective to 0.015 and certain things didn't fall on spec. It gives you a tolerance stackup of each culprit dimension, and it gives you a list of its units, tolerance, nominal, and sensitivity. Gives you that little graph or this analysis that we saw earlier, and it also displays, like I said, the percentage contribution of each of the offending parts. So very simple, very neat, and very quick to do a report to give to your QA team. And that's basically it. Let us just go back to our webinar. So that brings us to the end of this webinar. I'd like to thank you again for joining me. We're just going to leave a few minutes in if anyone's joined and listening and would like to have any questions answered regarding Inventor Tolerance Analysis. You're more than welcome to ask your question now. You can either speak in, remember to unmute yourself, or you can simply type it into our chat box here. I'm going to leave this last slide open and just give people time to ask questions. Okay, so if there's no questions, once again, I'd like to thank you all for joining us, and we will see you in the next webinar if you can join us again. Thank you so much. Bye bye.